So this video we shall be discussing Maxwell's third law. If you recall, we have already seen Maxwell's first law and Maxwell's second law. And please also go back and see to it that Maxwell's first law is based on Gauss law for electric field. Maxwell's second law is based on Gauss law for magnetic field. Now we are going to see Maxwell's third law, Maxwell's third equation, Maxwell's third equation, and this is going to be based on Faraday's law. So Maxwell's third equation, if you please remember, is going to be based on Faraday's law. So let us start with Faraday's law and go from it, right? So now I shall be writing Faraday's law. So Maxwell's, sorry, just a minute, give me a minute. Yeah, third equation will be based on Faraday's law, which I am going to write as my electromotive force, which I will call E, as equal to the rate of variation of the flux lines with the respective time minus d phi by dt. E is the electromotive force. Now I am going to give you an expression for E, I am going to give you an expression for phi and develop this equation. So electromotive force is given as the variation of electric field, okay, over a closed line, which means something like this. Over a closed line, how is the electric field varying? Gives you the electromotive force. So here I have an L to indicate that this is a line integral. Now phi we have already seen is equal to surface integral of B dot ds. We have seen it in the last equation itself. Now substituting both this, what will I get? Line integral of E dot dl is equal to minus surface integral of dB by dt into ds. So this is Maxwell's third equation in, that's right. This is Maxwell's third equation in integral form. So I shall now be concerned about Maxwell's third equation in differential form. So if you see here, this is different from the first couple of equations. I have a line integral which relates to surface integral. So now I shall be invoking Stokes' theorem. So according to Stokes' theorem, right, I shall be relating this line integral. So given any vector A, I can say that A dot dl, line integral of A dot dl, is given by surface integral of curl of that vector over a surface. So what do I mean by curl? Having a field, if my field is varying like this at an angle, it's going on varying like this, I'd say tell it the curl of the vector. If my field is varying like this without an angle, I cannot speak about a curl. Curl means varying in this angle. So curl of the vector. So applying the same analogy, what can I write? I can write this line integral of E dot dl is equal to surface integral of, let us say, curl of E over ds. So I'm going to substitute here in this place. So what will I get? So surface integral of del cross E dot ds is equal to minus surface integral dB by dt into ds. Again, both are surface integrals over an arbitrary surface ds. So I can write del cross E is equal to minus dB by dt. So this is my Maxwell's third equation in differential form. Okay, Maxwell's third equation in differential form. You see now the third equation is relating the variation in magnetic field to the electric field to the magnetic induction. So we have now seen the third law of Maxwell's equations. So next video we shall be seeing the fourth.